Hello, this is Spencer Wong, and I'll be introducing this computational demonstration, which is designed to be a pedagogical aid to the paper Attention in Natural Language Processing. And so the paper goes through lots of recent attention-based architectures and uses them to describe a general taxonomy for attention. However, it doesn't go into much detail about any of the architectures, and it can be pretty unclear how any of those ideas could actually be implemented. So what we do in this paper, this demonstration, is we show how a single head self attention model, as well as an extension of it, a multi head self attention model, can be programmed and trained on a real data set. So we start off by looking at the single head self attention architecture and describe what happens to an input set of vectors when you put it into that model. Along the way, we define functions for doing those things. Then the next step, since we want to be able to train the model on some real data, is we need to work out how to backpropagate the loss, where we use the cross entropy loss here. And so we want to find the gradient of that with respect to these learned parameters. And so after some work, we end up with these nice matrix-based equations. And being in matrix forms means that we can make use of NumPy during the backpropagation, and it shouldn't take too long. So the next step is we put together the single head self-attention model as a Python class. And now, so the code for doing this, what I've done is I've taken some of the code from Michael Nielsen's excellent online course on feed-forward networks. So what he does is he defines some code which creates a feed-forward network as a class in Python. So I've basically taken his code and emptied it out, but used it as a skeleton for constructing this self-attention model as a Python object, which is, I think, a nice way of keeping everything organized. So we can define the functions for stochastic gradient descent and backpropagation and everything in there. So then the next step is to actually train our model on some data. So we've put together a data set, and what exactly that is a spreadsheet, and each row is a group of words that all rhyme with each other. And so we're going to train our model to classify whether a pair of words rhyme or not. So to make a data set of pairs of rhyming words, we take each row and produce all permutations of the elements in the row, which produces a list of pairs of rhyming words. And we also need a list of pairs of words that don't rhyme. So what we do is we take the columns and take all permutations of two words from those. And in theory, none of these words in the columns should rhyme with each other. Then we convert those pairs of words into one-hot vectors based on their spellings. So we have a vocabulary of 27, the 27th symbol being a separator between the two words in a pair. And the reason we've chosen this dataset and this task is that it lets us have this fairly small vocabulary compared to if we were doing something like sentiment analysis or translation. It would require a vocabulary of tens of thousands of words, which is, I think, not computationally viable for me, at least. And so with that data set created, we're ready to train this single head self-attention model, which you do for 200 epochs, and we use a learning rate of 0.06, and we are just using the classic stochastic gradient descent, so no more complicated optimization algorithms. And we can see that some sort of meaningful learning appears to be happening. The performance is quite a bit better than random chance. It's not brilliant. However, it is a bit unclear what it actually is learning, because if we consider this input here, seal and box, it's saying that they almost certainly rhyme, which is not true. So it's learning something useful, but it's not clear whether it's learning to understand the sounds of letters and things like that. So then we go and extend the single head attention model to a multi-head self-attention architecture, which is the type of thing which is found in the popular transformer model. And basically, it's basically the same as the single head model, but does the same process multiple times in what are called different heads in parallel. And that allows it to view the data in different ways and put that all together at the end. And so to program that, we don't need to do that much work. We can quite easily adapt the earlier code. And instead of having parameter matrices, we just change them to lists of parameter matrices, where the lists contain a matrice for each of the different heads. And so then we put together an architecture of that form and train it. We train it for less epochs because it takes longer to train. And we also see that some sort of useful learning appears to be happening. Interestingly, the validation accuracy here, it's the maximum that occurs is actually a little bit lower than in the single head case, but it's unclear whether that is due to the architecture or the hyperparameters or just stochasticity, because there were previous runs where the performance was swapped. However, the purpose of this demonstration isn't to compare which architecture is better for this task. It's just to show how they can be programmed and implemented, which I hope we have done. All right, and that's it. We've just got some references here and some discussion on possible future, or not, possible extensions to this that could be carried out. All right, thank you.